Let us begin quietly, and let us place ourselves inside the broad landscape of abstract algebra. Earlier algebra often begins with familiar operations. We add, subtract, multiply, and sometimes divide. We notice patterns. We notice that certain sets of objects behave like the integers, or like rational numbers, or like matrices, or like polynomials. Abstract algebra asks us to look past the particular objects and to study the structure that makes these operations meaningful. Tonight, we move through three important regions of advanced abstract algebra: field theory, module theory, and Galois theory. Each of these regions has its own language, its own examples, and its own natural questions, but they are deeply connected. Field theory studies arithmetic systems in which division behaves well. Module theory studies generalized vector spaces where scalars may come from rings rather than fields. Galois theory brings fields and groups together, showing that the roots of polynomial equations have hidden symmetries. The theme running through all of this is structure. We enlarge structures. We decompose structures. We compare structures. We ask which transformations preserve structure. And again, abstract algebra teaches us that what first appears to be a problem about calculation is often, more deeply, a problem about symmetry. Let us move slowly. A field is an arithmetic system where the usual four operations behave in a very controlled way. We may add, subtract, multiply, and divide, with the one familiar exception that division by zero is not allowed. This is the calm and familiar world of rational numbers, real numbers, and complex numbers. In each of these systems, non-zero elements have multiplicative inverses. If we multiply by a non-zero element, we can undo that multiplication by dividing. This is one reason fields are so pleasant. They give us an arithmetic environment in which equations are often easier to manipulate. In a field, if a non-zero quantity multiplies something, we can divide by it. In a field, linear equations behave in the way we expect. Vector spaces, as they are usually introduced, are built over fields precisely because fields provide enough arithmetic freedom. Let us pause and reflect on this point. A field is not just a set of numbers. It is a setting for arithmetic. What matters is not the physical nature of the elements, but the rules they obey. Rational numbers form a field. Real numbers form a field. Complex numbers form a field. Certain finite systems also form fields, even though they may contain only a small number of elements. A field is therefore an abstract arithmetic universe. Now, once we have a field, it is natural to ask whether we can enlarge it. We may begin with rational numbers and discover that some equations cannot be solved inside the rational numbers. For example, there are polynomial equations with rational coefficients whose roots are not rational. If we want those roots to exist inside our arithmetic system, we must move to a larger field. This larger field is called a field extension. A field extension is an enlargement of a field, where the original field sits inside a bigger field. The bigger field contains all the old elements, and possibly new ones. The operations agree with the old operations where they overlap. In this way, field extensions are controlled enlargements of number systems. This idea is very important. We do not simply throw in new elements randomly. We enlarge a field in a way that preserves the arithmetic structure. If the original field was rational numbers, we might enlarge it by adding a square root that was missing. If the original field was real numbers, we might enlarge it by adding an element whose square behaves like -1. In doing so, we reach the complex numbers. It is worth repeating, a field extension is a larger field containing a smaller field. The smaller field is not destroyed. It remains present inside the larger one. The larger field simply gives us more elements with which to solve equations and express arithmetic relationships. One can think of field extensions as a way of making room. The rational numbers are beautiful and exact, but they are not large enough to contain every root of every polynomial equation with rational coefficients. The real numbers are much larger, but they still do not contain roots of certain equations that naturally lead to complex numbers. The complex numbers, in turn, are large enough to contain all roots of polynomial equations with complex coefficients. This is a remarkable fact, and it already points toward algebraic closure, which we will return to later. Finite fields give another kind of example. These are fields with finitely many elements. The arithmetic is not like the arithmetic of real numbers on a line. Instead, the elements cycle and repeat in a modular way. Yet, When the rules are arranged correctly, division by non-zero elements still works. This shows again that the idea of a field is structural rather than purely numerical. So the first picture is this. A field is a place where arithmetic is well behaved. A field extension is a larger place where the same arithmetic continues, but with additional elements. Often those additional elements are introduced because we want to solve equations that could not be solved before. Now let us think more carefully about the new elements we add to a field. Suppose we begin with a field and then consider a larger field containing it. An element in the larger field may be related to the smaller field in different ways. The most important distinction is between algebraic elements and transcendental elements. An element is called algebraic over the original field if it satisfies some non-zero polynomial equation whose coefficients come from the original field. In plain language, an algebraic element can be captured by a polynomial equation built from the smaller field. It may not belong to the smaller field, but it is not completely foreign. It is tied to the smaller field by an algebraic relation. For instance, when we enlarge the rational numbers by adding a square root that was not rational, that new element is algebraic over the rational numbers. It satisfies a polynomial equation with rational coefficients. The new element is not rational, but it is described by a rational polynomial equation. It is new, but it is not arbitrary. Let us say that again more slowly. An algebraic element is an element that solves a polynomial equation coming from the base field. It may lie outside the base field, but it is controlled by the base field. It is introduced as a root, as a solution, as something demanded by an equation. A transcendental element is different. A transcendental element is not the root of any non-zero polynomial equation with coefficients in the original field. It is not captured by polynomial algebra over that field. It escapes all such algebraic descriptions. The most famous examples arise when the original field is the rational numbers. Certain real numbers are not roots of any non-zero polynomial equation with rational coefficients. These numbers are transcendental over the rational numbers. They are not merely irrational. Irrationality means not rational. Transcendence means not algebraic over the rational numbers. That is a much stronger statement. It is useful to distinguish these ideas carefully. An irrational number may still be algebraic. Many square roots are irrational, but algebraic. They are roots of polynomial equations with rational coefficient. A transcendental number is also rational, but for a deeper reason. It cannot be described as a root of any such polynomial equation. Now, when an element is algebraic, there is a special polynomial associated with it called its minimal polynomial. The minimal polynomial is, in a sense, the simplest polynomial equation over the base field that the element satisfies. It is the most economical algebraic description of that element. It captures the essential algebraic relationship between the element and the base field. The minimal polynomial is important because it tells us how complicated the element is over the original field. It gives us a precise way of measuring the algebraic dependence of the new element. If we add an algebraic element to a field, its minimal polynomial governs many properties of the resulting extension. Let us pause and reflect. Field extensions are often built by adding roots of polynomial equations. Algebraic elements are those that arise in this way. Transcendental elements do not arise as roots of polynomial equations over the base field. Minimal polynomials give the simplest algebraic descriptions of algebraic elements. This distinction also helps us separate two related but different activities. One activity is solving equations inside a given field. Another activity is enlarging the field so that equations become solvable. If an equation has no solution in the original field, we may create or identify a larger field in which it does have a solution. This is one of the basic movements of field theory. The equation leads us to the extension. The missing root suggests a new element. The new element generates a larger field, and the larger field remembers the original field while making new solutions available. Let us now turn to finite fields. At first, the idea of a finite field may feel surprising. We are used to fields like the rational numbers, real numbers, and complex numbers, all of which contain infinitely many elements. But there are also fields with finitely many elements. These finite fields are among the most elegant objects in algebra. They are small, exact, and highly structured. A finite field is simply a field with a finite number of elements. It still has addition, subtraction, multiplication, and division by non-zero elements. The difference is that there are only finitely many possible values. Arithmetic in such a field must eventually repeat. There is a circular or modular quality to it. The simplest finite fields arise from arithmetic modulo or prime number. If one takes the integers and treats two integers as the same whenever their difference is divisible by a fixed prime, one obtains a finite field. The primality is essential here. When the modulus is prime, every non-zero residue has a multiplicative inverse. That means division works, and so the resulting system is a field. If the modulus is not prime, division may fail. There may be non-zero elements whose product is zero in the modular system. Such elements obstruct the existence of inverses. This is why prime numbers appear naturally in the simplest finite fields. But finite fields are not limited to prime numbers of elements. Their sizes are prime powers. That is, a number of elements in a finite field must be obtained by taking a prime number and raising it to some positive whole number power. Conversely, for every such prime power, there exists a finite field with that many elements, and it is essentially unique in a precise algebraic sense. Let us restate this gently. Finite fields do not come in arbitrary sizes. There is no finite field with just any chosen number of elements. Their sizes are governed by primes. A finite field has a size that is a prime power, and every prime power gives rise to a finite field. Why do prime powers appear? The reason is that every finite field contains the smallest prime field inside it. This prime field behaves like arithmetic modulo some prime. The whole finite field can then be viewed as a finite-dimensional vector space over that prime field. A finite-dimensional vector space over a finite field has a number of elements equal to a power of the size of the scalar field. Thus prime powers arise naturally from the combination of prime modular arithmetic and finite-dimensional vector space structure. This is a beautiful example of how algebraic ideas overlap. A field contains a smaller field. The larger field is a vector space over the smaller one. Counting elements then reveals a structural constraint. Size becomes a consequence of algebra. Finite fields can also be constructed using polynomials. One begins with a prime field and then uses an irreducible polynomial to create a larger field. In a way, this resembles how one constructs certain extensions of the rational numbers by adding roots of irreducible polynomials. The same idea appears again. We create new algebraic elements by forcing a polynomial to have a root. In finite fields, polynomial constructions are especially powerful. They allow us to build fields of prime power size. These fields are not merely theoretical curiosities. They are central in coding theory, cryptography, combinatorics, and computational algebra. In coding theory, finite fields provide the arithmetic behind error-correcting codes. Messages can be encoded as algebraic objects, and errors can be detected or corrected using polynomial structure over finite fields. In cryptography, finite fields support systems where arithmetic is easy to perform in one direction but difficult to reverse without special information. In both cases, the finiteness is not a defect. It is a feature. It makes the arithmetic computable, discrete, and reliable. Let us pause again. A finite field is a complete arithmetic world with only finitely many elements. Its size must be a prime power. It may be built from modular arithmetic and polynomial constructions. And although it is finite, it has a rich internal structure that makes it useful both in pure mathematics and in applications. We now return to polynomial equations. Suppose we have a polynomial over a field. It may not factor completely over that field. Some of its roots may be missing. Perhaps it has no roots at all in the original field. Perhaps it has some roots, but not enough to break the polynomial into linear factors. A splitting field is a field extension in which a given polynomial factors completely into linear factors. In plain language, it is a field large enough to contain all the roots of the polynomial. The polynomial, which may have been only partly understood in the original field, becomes fully decomposed in the splitting field. This is a very natural idea. If a field is too small for a polynomial, we enlarge the field just enough so that the polynomial fully splits. We do not merely ask for one root. We ask for all roots. The splitting field gathers all of them into one algebraic environment. Let us repeat this in another way. A splitting field is the field obtained by adjoining all the roots needed to make a polynomial completely factor. It is a controlled enlargement designed for one polynomial. It is not necessarily the largest possible field. It is not an arbitrary extension. It is tailored to the polynomial. For example, a polynomial with rational coefficients may have roots that are irrational or complex. Its splitting field over the rational numbers is the smallest field, in the appropriate sense, containing the rational numbers and all of those roots. Inside the splitting field, the polynomial is no longer partially unresolved. It has fully revealed its roots. The idea of a splitting field naturally leads to the idea of an algebraic closure. Instead of choosing one polynomial and adding all of its roots, imagine enlarging a field so that every polynomial over the field has all of its roots. Such a field is algebraically closed. An algebraic closure of a field is an algebraic extension that is algebraically closed. The complex numbers are the guiding example. Every non-constant polynomial with complex coefficients has a root in the complex numbers, and in fact factors completely over the complex numbers. This is one of the central facts of algebra. The complex numbers are algebraically closed, while the real numbers are not. For a general field, an algebraic closure is a field containing all algebraic roots that could arise from polynomials over the original field. It is, in a sense, a completion of the field with respect to algebraic equations. It is a place where polynomial equations become solvable as far as algebraic roots are concerned. It is worth repeating the distinction. A splitting field is built for a particular polynomial. An algebraic closure is large enough for all polynomial equations over the field. The splitting field solves one polynomial completely. The algebraic closure solves all polynomial equations, at least in the algebraic sense. There is also a subtle but important philosophical distinction between construction and existence. Sometimes we explicitly construct a field extension by adjoining roots. Sometimes we prove that an algebraic closure exists, even if we do not write down every element concretely. Abstract algebra often moves between these two modes. It constructs when construction is illuminating. It proves existence when the object is too large or too general to describe element by element. Let us pause and reflect. We began with fields as arithmetic systems. We enlarge fields by adding elements. Algebraic elements arise as roots of polynomial equations. Splitting fields gather all roots of a given polynomial. Algebraic closures provide a universe in which all algebraic polynomial equations can be solved. The movement is always the same, from a smaller arithmetic world to a larger one, guided by the need to solve equations. Now we shift from field theory to module theory. At first, modules may seem like a new topic, but they are closely related to ideas we already know. A module is a generalization of a vector space. In a vector space, vectors can be added to one another, and they can be multiplied by scalars from a field. In a module, the scalars come from a ring instead of necessarily coming from a field. This one change makes the theory much broader. It also makes it much more complicated. Let us begin with the familiar case. In a vector space, the scalars form a field. Because scalars can be divided when non-zero, vector spaces have a very clean structure. Every vector space has a basis. Any two bases have the same size. Linear maps can be studied using matrices. Subspaces behave well. Quotients behave well. Many things are pleasantly rigid. Modules look similar at first. They have addition. They have scalar multiplication. The scalar multiplication is compatible with the ring operations, but because the scalars come from a ring rather than a field, division may not be available. Non-zero scalars may fail to have inverses. There may be zero divisors. There may be torsion phenomena. Bases may not exist. Even when generating sets exist, they may not behave like bases. This is why modules are both flexible and subtle. They generalize vector spaces, but they lose some of the simplicity that fields provide. It is worth repeating, a module is like a vector space, but with scalars from a ring. This means modules inherit the intuition of linear algebra, while also reflecting the complexity of ring theory. They are linear objects over rings. Examples are everywhere. Every vector space is a module, because every field is a ring. Every abelian group can be viewed as a module over the ring of integers. Ideals in a ring are modules over that ring. Spaces of solutions, algebraic invariants, and many constructions in geometry and topology are naturally modules. Submodules are the module analogues of subspaces. A submodule is a subset that is closed under addition and scalar multiplication by elements of the ring. It is a smaller module sitting inside a larger one. Just as subspaces allow us to study pieces of vector spaces, submodules allow us to study pieces of modules. Quotient modules are also analogous to quotient vector spaces or quotient groups. If we have a module and a submodule, we can collapse the submodule to zero and study the resulting quotient structure. The quotient module records what remains after treating the submodule as negligible or identified with zero. Module homomorphisms are structure-preserving maps between modules. They preserve addition and scalar multiplication. They are the module version of linear maps. In fact, when the modules are vector spaces, module homomorphisms are exactly linear transformations. So we have a familiar pattern: objects, subobjects, quotients, and structure-preserving maps. This is one of the recurring grammars of abstract algebra. Groups have subgroups, quotient groups, and homomorphisms. Rings have ideals, quotient rings, and ring homomorphisms. Modules have submodules, quotient modules, and module homomorphisms. Let us pause and reflect on why modules matter. Modules give a common language for many mathematical situations where linearity is present but the scalar system is not a field. They allow algebra to speak about abelian groups, ideals, representations, linear operators, and more. They are one of the central languages of modern algebra because they unify many constructions under one framework. Modules remind us that vector spaces are unusually nice. They are not the whole story. They are the cleanest part of a larger theory. Modules are what happens when we keep the linear structure but relax the scalar arithmetic. Now let us discuss one of the great classification results in module theory, the structure theorem for finitely generated modules of a principal ideal domain. This sounds technical, so let us unpack it slowly. A finitely generated module is a module in which a finite list of elements is enough to generate the entire module. That means every element of the module can be built from that finite list using addition and scalar multiplication. In a vector space, this would correspond to finite spanning sets. But for modules, finite generation does not necessarily imply the existence of a basis. A principal ideal domain is a particularly well-behaved kind of ring. It is an integral domain, and every ideal is generated by a single element. The integers are the guiding example. Polynomial rings over fields in one variable are another guiding example. Principal ideal domains are not fields in general, but they are structured enough to support a powerful classification theory. The structure theorem says, broadly, that finitely generated modules of a principal ideal domain can be decomposed into simpler building blocks. This is a classification result. It tells us that such modules are not arbitrary mysterious objects. They can be broken into standard pieces. Let us say that again in common language. Under the right conditions, a finitely generated module can be understood by decomposing it. It has a free part, which behaves somewhat like a vector space, and a torsion part, which consists of elements killed by some non-zero scalar. The torsion part itself can be decomposed into simpler cyclic components. The details can be stated in different but equivalent forms, but the guiding idea is always decomposition into understandable piece. This theorem is powerful because it generalizes familiar classification results. For example, finitely generated abelian groups are exactly finitely generated modules over the integers. The structure theorem tells us that every finitely generated abelian group decomposes into a free part and a finite torsion part. This explains why such groups can be classified in terms of copies of the integers and finite cyclic pieces. The theorem also connects to linear algebra. If we study a linear operator on a finite-dimensional vector space, we can view the vector space as a module over a polynomial ring, where the variable acts by the linear operator. The structure theorem then leads to canonical forms for linear transformations. This is one deep reason why module theory illuminates matrix theory. Let us pause and reflect. The same theorem speaks to abelian groups and to linear algebra. That is a sign of a truly structural result. It does not merely solve one problem. It reveals that different problems share the same underlying algebraic form. The central idea is decomposition. Abstract algebra often tries to understand a complicated object by breaking it into simpler objects. Groups may decompose through normal subgroups and quotient groups. Rings may be studied through ideals and quotient rings. Modules may decompose into cyclic or free components. The structure theorem is one of the clearest expressions of this algebraic instinct. It is worth repeating, the structure theorem does not say that all modules are simple. It says that finitely generated modules over especially nice rings can be classified. The hypotheses matter. Over arbitrary rings, module theory can become extremely complicated. But over principal ideal domains, enough order remains for a beautiful classification. So modules give us a broader linear algebra, and the structure theorem tells us that, in favorable settings, this broader linear algebra still has a comprehensible architecture. We now arrive at Galois theory. Galois theory is one of the most beautiful bridges in mathematics. It links polynomial equations, field extensions, and group theory. It begins with a classical question: when can a polynomial equation be solved by formulas involving arithmetic operations and radicals? Historically, mathematicians knew formulas for solving general polynomial equations of low degree, but higher degree equations resisted similar formulas. Galois theory explains why. It shows that the solvability of a polynomial equation is governed by the symmetry group of its roots. This is an astonishing idea. A question about solving equations becomes a question about groups. A polynomial has roots. Those roots may lie in a splitting field. The field extension has symmetries, transformations that preserve the base field and respect all field operations. These transformations permeate the roots of the polynomial. A collection of such transformations forms a group, called the Galois group. Let us slow down. Suppose we have a polynomial over a base field. We form its splitting field, the field containing all of its roots. Now we consider all transformations of this splitting field that preserve addition, multiplication, and the elements of the base field. Such transformations are field automorphisms that fix the base field. Because these transformations preserve the base field and the algebraic relationships defined over it, they must send roots of the polynomial to other roots of the same polynomial. They cannot send a root to an arbitrary element. They must respect the equation. Thus, the roots may be permuted, but only in ways compatible with the field structure. The Galois group is a group of all these allowable symmetries. It is worth repeating in several ways. The Galois group is a group of symmetries of a field extension. It consists of transformations that leave the base field unchanged. It acts on the roots of a polynomial. It records which roots are algebraically indistinguishable from the point of view of the base field. This phrase, algebraically indistinguishable, is useful. If two roots can be swapped by a symmetry that fixes the base field, then the base field cannot tell them apart using its own algebraic language. They occupy symmetric positions in the extension. Galois theory therefore reveals a hidden group behind a polynomial. The polynomial has roots. The roots generate a field extension. The field extension has symmetries. Those symmetries form a group. The structure of that group reflects the solvability and internal algebraic structure of the original equation. This is the grand connection: equations, fields, and groups. Let us pause and reflect. In field theory, we enlarged fields to include roots. In group theory, we studied symmetries. Our theory says that when we enlarge a field by adding roots, the resulting extension has symmetries, and those symmetries explain the equation. The act of solving an equation becomes the act of understanding a symmetry group. This is why Galois theory feels so profound. It does not merely give a technique. It changes the question. Instead of asking only, "Can I write down the roots?" we ask, "What is the structure of the field generated by the roots, and what are its symmetries?" The central result of Galois theory is the fundamental theorem of Galois theory. This theorem describes a correspondence between certain intermediate fields and certain subgroups of the Galois group. Let us unpack this carefully. We begin with a field extension that satisfies the appropriate Galois conditions. There is a base field. There is a larger field. Between them, there may be intermediate fields. An intermediate field contains the base field and is contained in the larger field. It is a field sitting between the two. On the other hand, the Galois group of the extension has subgroups. A subgroup is a smaller group inside the full group of symmetries. The fundamental theorem says that intermediate fields correspond to subgroups of the Galois group. Each intermediate field determines a subgroup, the transformations that fix every element of that intermediate field. Each subgroup determines an intermediate field, the elements of the larger field fixed by every transformation in that subgroup. This is a beautiful reciprocity. Fields give groups. Groups give fields. Subfields correspond to subgroups. But there is an important twist. The correspondence reverses inclusion. Larger intermediate fields correspond to smaller subgroups. Smaller intermediate fields correspond to larger subgroups. At first, this reversal may seem strange, but it is natural. If an intermediate field is larger, then there are more elements that a symmetry must fix. The more elements a transformation is required to fix, the fewer transformations are allowed. Thus, a larger field has a smaller fixing subgroup. Conversely, a smaller intermediate field imposes fewer restrictions, so more symmetries remain. Let us repeat this, because it is one of the key ideas. More fixed elements means fewer symmetries. Fewer fixed elements means more symmetries. That is why the inclusion is reversed. The fundamental theorem of Galois theory is not merely a counting result. It is a structural dictionary. It lets us translate questions about fields into questions about groups, and questions about groups back into questions about fields. If we understand the subgroup structure of the Galois group, we understand the lattice of intermediate fields. If we understand the intermediate fields, we gain insight into the subgroup structure. This is the heart of Galois theory. Let us pause and reflect once more. We began with polynomial equation. We built splitting fields. We studied automorphisms that preserve the base field. These automorphisms formed the Galois group. Then the fundamental theorem revealed the correspondence between the internal field structure and the internal group structure. This is a deep unification. Fields and groups are not separate islands. In Galois theory, they mirror each other. One of the most famous consequences of Galois theory concerns solvability by radicals. Classical algebra asks whether roots of polynomial equations could be expressed using formulas involving arithmetic operations and extraction of roots. For equations of low degree, this is possible in general. For a higher degree, it is not always possible. Galois theory explains this through group theory. Roughly speaking, a polynomial is solvable by radicals when its Galois group has a certain kind of group-theoretic solvability. The precise definition of a solvable group belongs to group theory, involving a chain of subgroups with abelian quotient. But the guiding idea is that the group can be decomposed through layers of manageable symmetry. Again, we see the theme of decomposition. Just as modules over principal ideal domains can decompose into simpler pieces, certain groups can decompose into simpler layers. When the symmetry group of a polynomial is too complicated in the wrong way, no formula by radicals can exist. This is a profound negative result. It does not merely say that mathematicians failed to find a formula. It says that no such formula can exist in general, because the symmetry structure forbids it. Let us say that more gently. The obstacle to solving certain equations is not a lack of cleverness. It is a structural obstruction. The roots have symmetries too complex to be resolved by radicals. This is one of the great lessons of abstract algebra. Sometimes impossibility is not a failure. It is a theorem. It reveals a boundary in the mathematical world. Let us now slowly gather the themes together. A field is an arithmetic system where division by non-zero elements is possible. Fields provide clean environments for solving equations and doing linear algebra. When a field is too small, we may enlarge it. A field extension is such an enlargement, preserving the original field while adding new elements. Some added elements are algebraic. They satisfy polynomial equations over the base field. Their minimal polynomials give their simplest algebraic descriptions. Other elements are transcendental. They are not roots of any non-zero polynomial equation over the base field. This distinction tells us whether an element is algebraically controlled by the original field or lies beyond its polynomial reach. Finite fields show that fields need not be infinite. They have finitely many elements, but division still works. Their sizes are prime powers. They arise from modular arithmetic and polynomial constructions. They are central not only in algebra, but also in coding theory and cryptography. Splitting fields solve a polynomial completely by containing all of its roots. Algebraic closures go further, providing a field in which all algebraic polynomial equations have roots. These ideas express a central movement of field theory, enlarge the field so that equations become solvable. Then modules enter as generalized vector spaces. A module is like a vector space, but its scalars come from a ring rather than a field. This makes modules more flexible and more complicated. Submodules, quotient modules, and module homomorphisms mirror the familiar structures of subspaces, quotient spaces, and linear maps. Modules form one of the basic languages of modern algebra. The structure theorem for finitely generated modules over principal ideal domain shows that, in favorable cases, modules decompose into simple pieces. This theorem explains the classification of finitely generated abelian groups and connects deeply to canonical forms in linear algebra. It reminds us that decomposition is one of the guiding principles of algebra. Finally, Galois theory brings the story back to polynomial equations. We form a splitting field. We study its symmetries. These symmetries form the Galois group. The fundamental theorem of Galois theory tells us that intermediate fields correspond to subgroups of this group, with inclusion reversed. The theorem creates a dictionary between field structure and group structure. Let us pause and reflect one final time. Fields give us arithmetic. Extensions give us new elements. Polynomials guide those extensions. Splitting fields collect roots. Algebraic closures create worlds where algebraic equations are solvable. Modules generalize linear spaces and reveal how algebra acts on additive structures. Structure theorems decompose complicated objects into simpler ones. Galois theory reveals that roots of equations have symmetries, and that those symmetries control solvability. In all of this, abstract algebra is not merely a collection of definitions. It is a way of seeing. It teaches us to look for the operations, the preserved structures, the maps, the subobjects, the quotients, the decompositions, and the symmetries. A polynomial equation may look like a request for numbers. But field theory tells us that the equation may require a larger arithmetic world. Galois theory tells us that the roots of the equation may carry a hidden group of symmetries. Module theory tells us that linearity can survive even when scalars come from rings rather than fields. And the structure theorem tells us that, under the right hypotheses, complicated algebraic objects can be carefully taken apart. So we end where we begin, with structure. Abstract algebra asks us to move slowly from calculation to pattern, from pattern to structure, and from structure to symmetry. Fields, modules, and Galois groups are different voices in the same conversation. They tell us that mathematics often becomes clearer when we stop asking only what the objects are and begin asking how they relate, how they transform, how they decompose, and what remains unchanged. And with that thought, we can let the ideas settle. A field is a calm arithmetic world. An extension is a careful enlargement. An algebraic element is a root described by a polynomial. A transcendental element escapes every such polynomial description. A finite field is a small but complete arithmetic universe. A splitting field is a home for all roots of one polynomial. An algebraic closure is a home for all algebraic roots. A module is a generalized vector space over a ring. A structure theorem is a promise that certain objects can be decomposed. A Galois group is a symmetry hidden among roots. And the fundamental theorem of Galois theory is the bridge between fields and groups. These ideas belong together. They form one long, quiet movement through advanced abstract algebra, from arithmetic to enlargement to decomposition to symmetry, and finally to the deep recognition that solving an equation often means understanding the structure around it.